Welcome back. We are in the third chapter, bolted, riveted and welded joints, and this will be covering in three parts. The first part is the bolted joints. Threaded or bolted joints are temporary joints in the sense that they can be assembled and disassembled at any point of time. Threaded joints or bolted joints can be classified as a temporary joint. Now in threaded joint there are different types. First is a screw. This is fixed into a threaded hole in one of the components being assembled. So this is having only a thread and it goes into a threaded hole. Fixed into a threaded hole. Then we have a stud. Stud is a cylindrical rod which is threaded at both the ends. That is, it will be like this. Be a cylindrical rod. It will be both threaded at both the ends. And one end is screwed into a connecting component and but is fastened on the other end. So this is a cylindrical rod threaded at both the ends. And then we have bolted joints, which are nothing but joints which consist of a bolt and a nut which is fastened to the bolt. These are the different types of threaded joints. Typical method of fastening or joining parts use devices such as bolts, nuts, riveting locks, rivets, locking devices. Then we have pins, we have keys, etc. Threaded and bolted joint form temporary joints that we have already seen. Now, this threaded joint has got some advantages. The major advantages of using a threaded joint can be written as: the first one is this threaded joints are highly reliable in operation. They are highly reliable in operation and they are very convenient to assemble and disassemble. Then a wide range of threaded joints may be adapted to various operating conditions. Wide range of threaded joints may be adapted to various operating conditions. And finally, the threaded joints are relatively cheap to produce. Due to standardization. Because standards are available, so they can be easily manufactured in bulk quantities. The major disadvantage of this screw joint is advantage of the screw joints or bolted joint is the stress concentration in the threaded portion. The stress concentration in threaded portion. This is a major disadvantage of this threaded joints, and this becomes vulnerable. This will be very vulnerable to fatigue loading or the variable load conditions. So under fatigue load conditions, this becomes very vulnerable because we have seen that stress concentration is a very important parameter which causes failure for fatigue loading. Now we'll see what are the major thread standards and definitions. Now we'll see what are the major thread standards and definition. The major definitions which include in the thread geometry are the thread has got different diameters which are shown in this figure, like major diameter, minor diameter, pitch diameter, such that. So we have major diameter. I will say D major is the largest diameter of a screw thread. Then we have the minor diameter, D minor, which is the smallest diameter of a thread. Then we have something called pitch diameter. This is important. As dP. This is a theoretical diameter between between the major diameter and the minor diameter. And this is the diameter at which the ridges of the bolt are in complete touch with the ridges of the corresponding nut. So when a bolt and nut is tightened, it is this diameter at which the surfaces will be in full touch, full contact with each other. Then we have crest, which is nothing but the top surface of the thread, shown in the figure. Then we have root, which is nothing but the bottom surface of the thread, which is created by the flanks of the thread. These are the flanks of the thread, and the bottommost surface which is created by the between the flank is called the root. Created between flanks of adjacent thread. Then we have depth. Then pitch is the distance between two thread. Pitch by P, distance between adjacent threads. Then we have a depth of thread. Depth of thread is the perpendicular distance between the crest and root. Perpendicular distance between crest and root of the thread. That is, in this figure we can say it as this distance will be the depth of the thread. Now there is another important parameter called lead. Lead, denoted by letter L, is the distance the nut moves in parallel, the distance which the nut moves in parallel to the screw axis when given one turn. That is, when the thread or when the bolt or nut, when it is given one turn, how much is the distance moved parallel to the screw axis? It is called lead. It may be same or different than the pitch of the thread joint. We have something called multiple thread joints. Multiple threaded screws. They are one having two or more threads. They have two or more threads cut beside each other. And the example is so multiple threaded screws may be having two or more threads cut beside each other. And for example, in a triple threaded screw, is one. In a triple threaded screw, the lead L is equal to 3 times the pitch, because it has got 3 threads which are cut next to each other, so it can move 3 times the pitch. Pitch is the distance between the adjacent threads. So in different types of threads are available in market, mainly metric thread, unified thread systems, Acme thread, square thread, knuckle thread, buttress thread, etc. In our place, most commonly used is a metric thread. Metric thread is most commonly used in India, and metric threads are specified by writing diameter and pitch in millimeter. For example, M12 by 1.75 means that the nominal dia is 12 mm and the pitch of the thread is 1.75 mm, and the letter M designates it's a metric thread. And square and Acme thread are also different types of thread, and they are mainly used on power screws where power is transmitted. Square thread, we know it will be like this. Where this distance, that is the pitch, this height is P by 2, and this width, this is also P by 2, where P is called the pitch. Pitch is the distance between the adjacent threads. Similarly, in Acme threads, it's similar to the square thread, but it has got tapering portion. And here, the pitch is the distance between the two adjacent threads. This is P. And if this is the pitch diameter, this distance will be P by 2, and usually this angle of the Acme thread is 29 degree. These are the different designations which are used in threads. Basically, metric thread, Acme thread, and square thread. This is Acme thread and this is square thread. Acme thread and square thread are basically used in power transmission. It is basically used in power screws. So next we will see what is power screw. Okay, now we will see what is a power screw. Power screw is a device used in machinery to change the angular motion into linear motion. These are device used to change the angular motion into a linear motion. An application of power screw is a power driven jacks, that is hydraulic jacks are there. These are the application of this power screws. Hydraulic jacks which are used to lift heavy objects, example of power screw. Power screw applications. Now this figure shows a square threaded power screw with single thread having a mean diameter of dm. This is a mean diameter, and pitch is P. That is the distance between this thread. This thread to this thread will be the pitch. The pitch. Now we need to find an expression for the torque required to raise the load and another expression for the torque required to lower the load. Now what we do is we unwind one of the thread of this power screw. When one thread is unwound, we get this distance as pi dm and this length will be L. It's a single threaded screw, so L will be equal to P. If it's a multiple threaded screw, it will become L will become the case for the raising of a weight, that is, we have the F is the force acting downwards, that is the weight of the component which has to be raised. N is a normal reaction due to the inclined surface of the screw thread. And since we have to raise the load, we have to apply a force PR. Actually, this force PR will be applied over this surface, and it will be rotating this screw about the center line. And when you apply a force, when it tries to lift the body up, you have the frictional force acting in the opposite direction. Similarly, when you try to lower the weight, the load is applied in this direction, and since it comes down, the frictional force will be acting in the upward direction. For these two cases, we need to find the expression for the torque required to raise the load as well as lower the load. So we'll take the first case. In this case, what we do is we apply the static equilibrium equation, that is sigma Fx equals 0 and sigma Fy equals 0. And equating all components of force in x direction, we get sigma Fx equals PR minus n sin lambda minus mu n cos lambda, and this becomes equal to 0, and sigma Fy will be equal to minus F, since it is acting in the downward direction, minus mu n sin lambda plus n cos lambda equals 0. From these two equations, what we can do is we can take the n outside from the second equation. So equation 1 and equation 2. Equation 2 will give n as F by cos lambda minus mu sin lambda, and this value of n will plug in the equation 1. So we get the raising load PR is equal to F into sin lambda plus mu cos lambda divided by cos lambda minus mu times sin lambda. Here mu is the coefficient of friction and lambda is the helix angle or thread angle. Or we will say not helix angle, it is a lead angle. So we get the load, the force required to raise the load will be given as F by F into sin lambda plus mu cos lambda divided by cos lambda minus mu sin lambda. Dividing the numerator and denominator by cos lambda, we get the relation that P R equals F into mu plus tan lambda, and we can get from the diagram, from the triangle, and from this triangle we can get that tan lambda is equal to L by pi dm. So this we will substitute in the below equation. Tan lambda is equal to L by pi dm. So we get PR is equal to F into mu plus L by pi dm divided by 1 plus mu L by pi dm. This will be the load required to raise the weight. Similarly, we can find the expression for torque also. Now the torque will be nothing but, the torque required to raise the load will be nothing but PR into dm by 2. I told that this force is applied in this direction. It will be applied over this surface, and the torque required will be, and it will be rotating the component about the center. So therefore torque will be this raising load into the mean diameter by 2. So this will give TR, the torque required to raise the load, as F into dm by 2 into L plus pi mu dm divided by pi dm minus mu into L. This is the torque required to raise the load. Similar expression we have to find out for lowering of the load. Similarly, we have to find an expression for the load force required and the torque required to lower the load. Here also we do the static equilibrium equation, which gives sigma fx equals minus PL, since it is acting to left side, minus n sin lambda plus mu n cos lambda equal to 0. Sigma fy will be equal to minus f plus mu n sin lambda plus n cos lambda is equal to 0. So similarly, as we have done in the above case, we take the normal, we try to eliminate the normal reaction from the expression. So finally we get the lowering load is equal to F into mu cos lambda minus sin lambda divided by cos lambda plus mu sin lambda. Now we can divide it by sin lambda by cos lambda throughout. This will be giving F into mu minus L by pi dm divided by 1 plus mu L by pi dm. This is the expression of the force required to lower the load. Similarly, therefore, we have the torque required to lower the load will be equal to PL into dm by 2, which will be nothing but F dm by 2 into mu minus, or we can write this will be equal to F dm by 2 into pi mu dm minus L divided by pi dm minus mu into L. This will be torque required to, it will lower the load PL, and this will be the force required to lower the load. In this expression, mu is the coefficient of friction, L is a lead, dm is a nominal diameter. This we have already seen. Now this we have got the expression for lowering the torque required to lower the load. When a positive torque is obtained from TL, that means we have to apply some extra load to bring the load down, then the screw is said to be self-locking. The self-locking is a case where TL is positive. If the torque required to lower the load is negative, that means no load need to be, load is not required to bring the weight down. It comes down by itself. Therefore, the condition for self-locking should be pi mu dm should be greater than L, or we can say mu should be greater than tan lambda. This should be the condition for self-locking. So I'll write this is the condition for self-locking of power screws. Self-locking means the weight will not come down by itself. It needs an extra load or extra force for lowering of the weight, lowering of the load. So if the angle of friction is given as phi, then we have mu is equal to tan phi. Then we can say the condition for self-locking should be tan phi should be greater than tan lambda, or which gives the angle of friction should be greater than the lead angle, where phi is the angle of friction. So if the angle of friction is greater than lead angle, then it is a self-locking system. That is, friction is greater than the lead angle. So extra load is required to overcome the friction also. Now we can derive an expression for efficiency of the screws. The efficiency of the power screws E can be written as the ratio of TO by TR, where TO is nothing but the torque required to raise the load with no friction, with mu is equal to 0. If the friction is not present, if there is no friction at all, what is the torque required to raise the load? That is given as TO, and TR is the torque required to raise the load under general circumstance. So this becomes the efficiency E is equal to TO by TR, that is equal to FL by 2 pi TR. So this is the efficiency of the power screw, where F is the load, the weight of the component or load to be raised, L is the lead angle of the power screw, and TR is the torque required to raise the load. So we get the efficiency E as this. So that is about the power screw and the applications. In most of the cases, square thread are used for power screws, but in many cases Acme thread is also used. In fact, it is used more than power square threads because of ease of manufacturing. And the another advantage will be there will be more friction in the Acme thread because of the angle of contact. So with this we come to the end of power screws. Now we will see, before coming to the end, we will see what are the stresses coming in the power screw. So we will see what are the stresses which are coming in the power screw. One is the axial stress, which is coming to the load due to the load F. So the axial stress in the body, which is given by sigma, which will be equal to F by A. That is 4F by pi dm square. Or we can take it as dr, where dr will be the minor diameter or the root diameter. So sigma is equal to 4F by pi dr square. This is the axial stress coming in the power screw. Now the transverse shear stress tau will be equal to 3 by 2 V by A. This we have already seen. This is actually happening due to the bending effect. That is, when you have a power screw like this with a thread here, where this distance is P by 2 and this distance is P by 2, and this is the load F. Load F. And this F will be acting in this portion, and it will cause a bending about the central axis. And because of this bending, they will have a shear stress distribution in this portion of the thread. The shear stress distribution, as we have seen in the beams, will be equal to 3 by 2. Since it's a rectangular cross section, the maximum shear stress will be 3 by 2 V by A, where V is the shear force. Shear force is nothing but F here. So this will be equal to 3 by 2 F by the shearing area will be pi dr. That is, the pi dr into P will give this area between the threads, between two successive threads. This will give the pi dr into P will be this area, and into N will give the total area which is getting this shear stress, where N is a number of threads. Here N is a number of threads, P is the pitch,